Hello, welcome everyone. In this video, I'm going to work out on the instantaneous rate of change or the derivative of the function. Okay, so let's go over this this diagram. Okay, first of all, we're going to take a look at it, this right here. Let's look at this expression. We have limit as h goes to 0 of f of x plus h minus f of x divided by h. So basically, the limit of this ratio as h approaches to 0 is going to be the derivative or the instantaneous rate of change. So if we look at this diagram right here, we see a curve and then we see these 2 points. Okay, so this is our interval, and the line that's connecting the interval, the slope of this line represents the average rate of change over this interval, that is between x and x plus h. So the length of the interval is h. So the distance from this point to this point right here is h units away. Okay, so let's write down the slope of this line first. So we know the slope definition: m equals delta y over delta x, which is rise over run, which is y2 minus y1 over x2 minus x1. So I'm going to mark the points. So x plus h is x2, and this right here, f of x plus h, the y value is going to be the y2, and f of x is y1. So y1 equals f of x. That is the function value at x equals x, and then we have x is going to be our x1 right here. X is going to be equal to x1. So now let's go ahead and plug in this right here. Y2 is going to be f of x plus h minus y1 is f of x divided by x2 is x plus h minus x1 is just x. Then we go ahead and simplify this. We have f of x plus h, so this is x, plus h minus f of x, and divided by, when we simplify this, x is gone and we're just left with h. So we get some kind of similar expression like this one right here, except that here the limit as h goes to 0. So when we go from average rate of change to instantaneous rate of change, that's what happens. That means we're reducing the interval size. So we're bringing this point closer and closer to this point right here. So, we're moving closer to this point. So there's a movement down this way. What is happening every time we are moving closer to this point, our h is getting smaller and smaller. So h, this is new h, and if we come right here, the new h is going to be like from here to here. And as we go close and close to 0, so as we bring it really close to 0, so what happens? It becomes so close that the line that connects these 2 points is almost tangent to this point right here. So this is the definition of the derivative, that as it becomes so small, the line that joins these 2 points is the tangent line. So the slope of that line represents the instant rate of change that is happening at this particular point, and that is the definition of the derivative as well. Like, the limit of this particular ratio as h goes to 0 is going to define the derivative of this point, function at this point. Okay, so for the derivative to exist, the function has to be differentiable, and it has to be continuous. So these are the two things, main things that we have to remember, and we'll go into more details later on. So it has to be differentiable and continuous. So one more time, the derivative of the instantaneous rate of change is like when h becomes so small, the 2 points are almost so close together, are really close, that the line connecting them becomes a tangent line to this point, and the slope of that tangent line represents the instantaneous rate of change at the point x, or it's called the derivative of the function at that point x. So limit as h approaches 0 or goes to 0 of this ratio is basically the derivative of the function, or the instantaneous rate of change of that function at that point. So let's work out an example. So we have this function right here. We want to find the derivative, or the instantaneous rate of change of this function, so using the definition of the derivative, which is right here. So I'm going to go ahead and plug in the values into this particular ratio. So for x, wherever we have x, we're going to plug in x plus h. So we're going to get the f of x plus h. Let's get that. That would be 2x plus h. So I substituted x plus h for x right here, because we are evaluating the expression at x plus h, and we have plus 5. Okay, this plus 5. And for f of x, it just stays the same. So in parentheses, we have 2x plus 5 and divided by h. And of course, the limit as h goes to 0 of this ratio. That defines the derivative of this function. So let's go ahead and simplify it further. So we have 2x plus 2h when we distribute 2 inside, plus 5 minus, when we have negative and there's no number after that, that means there's 1 there, so it's a negative 1, and when it multiplies with 2x, it becomes negative 2x. And then negative 1 multiplies with 5, it becomes negative 5. So when there is a negative outside, you can see the sign inside changes. 2 was positive, but when we distribute negative, it becomes negative, because negative times positive is negative. And 5 was positive, but multiplying with negative became negative. So if you have a sign outside the parentheses terms, and you're going to distribute the negative inside, you're going to change the sign inside the parentheses term when you finish your distribution. And then we go ahead and divide this by h as limit as h approaches 0. So limit of this function as h approaches 0. Okay, now let's go ahead and simplify it further. Let's eliminate some terms. This 2x will cancel this negative 2x. 5 will get rid of this negative 5. So you're left with 2h over h. And then we can further simplify it, just canceling h in the numerator and denominator. They cancel each other out. You're left with just 1. So 2 times 1 is equal to 2. So the limit as h goes to 0 of this function is 2 right here. This is our final answer. Alrighty, that would be it.